Alright, we're moving forward in Chapter 6, which is, for the most part, about SN2 reactions and the different aspects of SN2 reactions. And last time we ended on the leaving group, and we were talking about, like, you know, what different kinds of leaving groups, what makes good leaving groups. And generally speaking, there are things that are stable when they fall off. They're stable. I'm not going to review everything, and but just real quickly, we'll review a couple of the key concepts. That leaving groupability is roughly correlated to the stability of the leaving group once it's kicked off. And that kind of makes sense, that if a nucleophile kicks off a leaving group, that things that are stable would maybe make this more happy. Yeah, that's true. So best leaving groups are good at stabilizing a negative charge. So things like iodine and, you know, electronegative things, maybe if it's stabilized extensively by resonance, all of those things would make a good leaving group. Okay, so of this series, you know, if you consider the acids, HI is the strongest acid, and that means I minus is the most stable thing. Alright, this is all kind of review from last time. And then as you go through the series, HF is the very weak acid. And that's due to a lot of things about the structure of F minus. It's just concentrated charge density, and the negative charge is concentrated over a very small area, and that makes it very unhappy. Iodide, the reason I minus is so stable is because it's a huge atom, and the negative charge is distributed over a big area. Okay. We also mentioned a couple sort of novel leaving groups. This is they contain S double bond O, and actually another oxygen, and then some R group, or, you know, CH3 is one of them. It's called methane sulfonyl, or mesyl, or MS, and MS can be an abbreviation for the whole thing. It's a good leaving group. Nucleophile kicks it off, and then you in this case it's a secondary substrate, so you get inversion. But yeah, why is this thing kind of stable? It's stabilized by resonance, because you can distribute the negative charge all over the place. Okay. That's just an abbreviation of how else that might look. OMS, nucleophile kicks it off. Yeah, simple SN2 reaction. And a little bit more review from last time. Another one of those sulfur-containing leaving groups. Instead of CH3, it has a CF3. And that one is called, rather than methane sulfonyl, it's called Trifluoromethane Sulfonyl, and its funny name is triflate. So when people refer to triflate refers to this S double bond O CF3 thing, and and it does not refer to the oxygen. The oxygen is part of the leaving group, but triflate refers to that fragment. But you are pretty much always conjugated through an oxygen. So it's oxygen, then you have the triflate group. Overall, it's a good leaving group. Nucleophiles kick it off, and you get products like that. And then, of course, the leaving group is extensively stabilized by resonance. Okay, and this just shows it in another abbreviated form. You have a cyclohexane with a O triflate. Nucleophile kicks it off, and you get the triflate anion as a leaving group. All right. Okay, and then we have just one more example of this idea. This is all from last time. This structure is called toluene. Methylbenzene is called toluene, Toluene. Well, anyway, there's another leaving group structure called toluene sulfonyl. It's called Tazyl, or TS. Okay, and so this, in this case, the nucleophile attacks, kicks off this Tazyl leaving group, and you get the product. It's just another SN2 leaving group. All right, so that's all from last time. there's an abbreviation also of how a nucleophile would kick it off. And the thing that falls off is OTS, or TSO minus, TSO minus, all right? Okay, so we just basically, now we're moving on to the new stuff. So we're talking about 7, SN2 reactivity, still, leaving group. And we basically just said, oh yeah, that leaving group ability correlates to stability of the leaving group once it's departed. Leaving group ability correlates to the stability of the leaving group once it is departed. And we just said that, we explained that, and how if things stabilize the leaving group, it makes it a good leaving group. Next thing is kind of like a simple extension of that, is that weak bases are good nucleophiles. Sorry, I misspoke. Weak bases are good leaving groups. That's what I was trying to say. Weak bases are good leaving groups. Alright, so that's kind of another way of saying that leaving group ability has to do with the stability of leaving groups. Because things that are stable will typically be weak bases, because they don't have an interest in getting a proton. Okay, so examples. A couple weak bases. Weak bases are stable anions. Examples: I minus. I minus is a kind of huge atom with a dispersed charge density. It's a weak base. It's also stabilized by electronegativity. It's on the right side of the periodic table. Other things that we talked about, like methane sulfonate. It's a weak base, and that's due to just being a relatively stable thing. Resonance stabilizes this. We talked about resonance stabilization before of these things, but yeah, there's a lot of resonance stabilization. You can draw a bunch of resonance structures. O minus distributes among all the oxygens, etc. All of these things are nice leaving groups. All those things are nice leaving groups. Strong bases, stronger bases, are going to be good leaving groups or bad leaving groups? The answer is that weak bases are stable anions. So our strong base is going to be more or less stable, and strong bases are typically less stable. And when they're less stable, they have less of a desire to be just kicked off as a free ion or whatever. So things that are less stable don't want to be kicked off. They're going to be terrible leaving groups. Examples are fluoride, which we've already mentioned. Fluoride is really tiny, concentrated charge density, and it's not a very happy thing. Also things like alkoxides, like O minus CH2CH3, O minus CH2CH3, these are called alkoxides, which we talked about before. They're actually kind of strong bases and not very stable, and that's part of the reason they're strong bases, because they want to take a proton. Things that are kind of unstable, that are negatively charged, have incentive to get a proton because that makes them more stable. Okay, so strong bases are less stable, and these are generally bad leaving groups. Bad leaving groups. Okay. How to recognize weak bases. How do you recognize a weak base? Well, we have acidity tables, which tell you pKa, and that's actually one way to identify weak bases, and we'll see that in a second. Okay, so in generally speaking, though, you could say that the stronger ch6, that's X would be the leaving group with a proton on it. The stronger ch6 is as an acid, and that would suggest a low pKa value. The stronger ch6 is as an acid and having a low pKa, the weaker X- is as a base. Okay, and when that's the case, X- is a good leaving group. Okay, so that's it in a nutshell. So if you have a good pKa table, you can identify the good leaving groups. All right, so let's look at the pKa table. Okay, so this is a table. It's on the public website as a PDF file. You can download it, maybe stick it into your notes or whatever. It's reproduced from table 6.4 in the book, but it's a good little summary of leaving group ability and how it relates to pKa. All right, so when we think about pKa, we think about acids, right? So what are some acids? Those are some acids to consider, and we'll show the pKa values in a second, but you'll see that HI is the strongest acid, HBr, HCl, sulfuric acid, H3O, hydronium ion, methane sulfonic acid, and then we have worse and worse acids, HF, acetic acid, HCN, methanol, methanol, etc., etc. All right, so what we'll see though is the conjugate bases of things near the top are going to be better and more viable leaving groups. Okay, so let's show the pKa values, and this is all in it's on that PDF. You can download this, print it out, and we see that like HI has a very low pKa, -10, HBr -9, HCl -8, etc., etc. And then we've gradually worked your way to these things that are just terrible acids. HF is pretty bad. Even acetic acid, which is a carboxylic acid, is a higher pKa, hydrogen cyanide, methanol, etc. And as you move your way down, eventually these are extremely bad acids, like H2 is a very, very, very weak acid, and that's due to instability of the conjugate base. Okay, all right. So then we think about like what would the corresponding leaving group be when we consider these acids. So like I-, we know that's a great leaving group. We've talked about it a bunch. We've used it a bunch. Br, Cl. This one's maybe a little less common. Water can be a leaving group once in a while. And also these guys are close to like methane sulfonyl. Remember mesyl? Triflate and tosyl. Mesyl, triflate, and tosyl. The methane sulfonyl and the trifluoromethane sulfonyl and toluene sulfonyl. All those kind of fancy leaving groups we just saw. And then we keep going. F-, and what we're getting at is these top things are like considered good leaving groups, and the leaving group ability just goes down and down. So fluoride is a worse leaving group. Acetate's a bad leaving group, cyanide, etc., etc. The worst leaving group on this chart would be H-. And you can imagine, like, is something just going to come and kick off H-? You haven't seen that. You've always seen good leaving groups like chlorine or bromine or something like that, right? Okay, so I just kind of put the cutoff of like good leaving groups as about this middle point. And that's pretty typical. And most commonly, the ones that you see in chemistry are going to be the halogens like I-, Br, and Cl. Fluoride doesn't cut it. It's not a good leaving group, okay? And also the methane sulfonyl, trifluoromethane sulfonyl, and toluene sulfonyl, all of those are considered pretty good leaving groups. All right. And then, oh yeah, so leaving group ability kind of increases as you go up, and then basicity kind of goes downward. Basicity goes downward, so that's like the weakest base, and among this series, oh, that's the strongest base, right? So basicity and acidity are kind of inversely correlated, as you expect also. Okay, great. All right, so then let's just look at the bottom here of this chart and of just like kinetically favorable SN2 reactions, noting that that's a good nucleophile. We'll talk about nucleophiles in a bit. Sodium azide is Na+, N double bond to N double bond to N. Good nucleophile. N double bond to N double bond to N. It's a great nucleophile, and this is a fast reaction. Azide kicks off the iodide to make propyl azide. Propyl iodide to propyl azide, and then the Na+ just doesn't do anything. It just follows the leaving group, in this case iodide. So these are favorable SN2 reactions with good leaving group: iodide, bromine, and chlorine. Methane sulfonyl or methyl, same thing. And then we have the disfavorable ones, and this is as you get basically to the bottom of the table above. None of these reactions work. These are not good SN2 reactions because you have a bad leaving group. Fluoride, methoxide, hydroxide, ammonia, H. H is the worst leaving group in the universe, possibly. Okay? And yeah, these are just disfavorable because you have really bad leaving groups. Okay, so these don't really go. All right, so the main thing, what else does it say? Yeah, so looking above again, we start with fast, you end up with kind of slow, but it's still viable. These actually work. And then it gets slower and less viable to H- being a leaving group, which is the worst leaving group in the universe. Okay. So this is a good chart that summarizes acidity and how acidity relates to leaving group ability, and also you could just say leaving group stability as the leaving group departs, right? And then these are examples that show kind of good leaving groups, the halogens and the sulfur-based ones, and then bad leaving groups, which are fluoride and then these other things that just are not stable when they get kicked off. Alright, so we're done with the leaving group. I think we understand, or we at least have a list of leaving groups that are in our mind that are kind of good leaving groups. Halogens and then the sulfur-based ones. Let's talk about nucleophile now. SN2, reactivity. Remember the N is a little bit subscripted there. The nucleophile. What makes a good nucleophile? What makes a bad nucleophile? Alright. So, a couple things. First is that if you increase the negative charge, or like you go from a neutral thing to a negatively charged thing, so you go from like neutral to negative or something like that, that will increase the rate of nucleophilic attack. Kind of makes sense because you're attacking something that's delta positive, right? And if you're or positive or delta positive, so what's better, something that's negative or something that's not negative? And the answer is, yeah, things that are negative are going to react better and more efficiently as SN2 nucleophiles. Okay, so a couple examples of this. If I have hydroxide and chloroethane versus water and chloroethane, who is the better nucleophile? And remember, of course, we have delta minus and delta plus on both of these. Who's the better nucleophile, the negatively charged one or the neutral one? And the answer is, of course, the negatively charged one will be. Alright, I'll show one mechanism. Well, I can show both mechanisms. They're both easy. The mechanisms are easy, right? 2 arrows each, nucleophile attacks, kicks off the leaving group. Alright. So they don't make the same exact product, because in this case the product's actually plus. Neutral plus neutral makes plus, and then you have the chloride leaving group and the chloride leaving group. Okay, cool. And who's the faster one? Probably the top or the bottom. What do you think? If the negative charge makes it better and faster, it's probably going to be the top is faster, slower. Not that difficult. Okay, another example. Same kind of situation, but we have H2N minus. We'll just keep the substrate fixed. Chloroethane. Okay. Delta minus, delta plus, delta minus, delta plus. Alright, and then what are the products? What are the mechanisms? Same thing. NH2 minus attacks, kicks this off. In reality, it's a little more of a backside thing, but I can't show it too easily with these figures. But okay, there we go. What are the products? NH2 attacks, now you have H2N, and then here it's H3N. Redraw, make it look nicer. Okay, cool. What is the charges? Well, when a negatively charged attacks the substrate, it's going to be negative plus neutral makes neutral plus negative. Here it's neutral plus neutral makes positive, so neutral plus neutral, and then the right side should balance in charge. So it's going to be neutral plus neutral makes positive plus negative. Where's the positive charge? Well, just like above, same kind of thing happened. Water attacked, and it's on the nitrogen. Okay, so who is the faster reaction? The one with the negative nucleophile or the one with the neutral nucleophile? They basically do the same thing in terms of attaching nitrogen, but which is faster, the negative charge or the neutral? And the answer is the negative charge one. Slower. That makes sense. That's what we were arguing, that when you increase the negative charge, the rate of the reaction goes up. The reasoning for that is pretty obvious. The nuke is attacking an electrophilic carbon. It's either delta positive or, you know, it could be fully negative depending on what you're doing. Usually with SN2 it's a delta positive, a partially positive thing. And so the more negative the nucleophile, the more negative the nucleophile, the faster. Totally makes sense. Alright? Totally makes sense. Okay, let's just real quickly show some commonly seen negatively charged nucleophiles. So you see these over and over and over, so it's good to just show them. Just some kind of miscellaneous reactions. Alright, so... And I'm just putting my substrates on the left and nucleophiles on the right. That's all arbitrary. Na plus... We showed this already. What's it called? N double bond N double bond N. We gave it a name. What's the name? It's called azide. You could call this overall molecule sodium azide. Sodium azide. What are the charges? If you have to calculate them, or just kind of remember that it's negative, positive, negative, negative, positive, negative. And the overall sodium azide molecule would be neutral, Na plus, and then this thing's net negative. So, but the nucleophile itself is a negatively charged nucleophile. And what's the product? Ethyl azide and Br minus. Okay. And what's the mechanism? Circle, unpair, attack, kick off. All right. If you want to draw your partial charges in, you can do that. Another one, and my goal here is to just kind of show a bunch of different negatively charged nucleophiles, just so you're not surprised by them. Let's draw iodopropane as a substrate, and then K plus. Oh yeah, and this, sorry, the sodium above. The sodium is a spectator ion. It doesn't really do anything, but it will kind of coordinate with the leaving group at the end. Notice another thing. I'm not showing any arrows of like that thing forming. There's no mechanism arrows here. The only mechanism arrows to really show are the nucleophile attacking and then kicking off the leaving group. I don't show like Br minus arrow to sodium because it's an ionic interaction and it's not really an interesting part of the mechanism. Okay, so I'm not really, no arrows related to the spectator ion. It just kind of, you know, goes away here and sort of comes back there. All right. K plus Cn minus. K plus Cn minus. Well, the Cn minus, you might know from Gen Chem, it's called cyanide. K plus is potassium cyanide. So we have potassium cyanide, K plus Cn minus. Well, that's another example of a good negatively charged nucleophile. The Cn minus attacks, circle unpair, and what do you get? Attacks, attaches, forms a CC bond. It actually forms a carbon-carbon bond. You get carbon C triple bond N, and then what's the byproduct? K plus I minus, potassium iodide. Alright, what's the functional group that we just created? It's not a cyanide, it's called a nitrile. A nitrile is that functional group. Okay? Alright, what else? Our goal is just to rapidly show some different negatively charged nucleophiles. And just, you know, miscellaneous reactions of SN2 reactions, right? Okay, I made it scary. I'm using mesylate, which is one of our other good leaving groups. And let's use this negatively charged nucleophile. Na plus, S minus, C triple bond N. Okay, this is maybe a little less common, so memorizing the name of this is not critical. It's called thiocyanate. Thiocyanate. But it's just another good SN2 nucleophile. Where do you think the nucleophilic atom is? I don't know. Maybe the S minus can attack. Very nice, simple mechanism. This overall molecule with a sodium would probably be called sodium thiocyanate. Sodium thiocyanate. Thiocyanate. Say that 10 times very rapidly. I probably could not. Okay, so what's the product look like? So now the sulfur attacks here, it kicks off the leaving group. Interestingly, the methyl is still there and is pointing towards us. Where does this attack and what does the stereochemical result look like? Well, this attacks from the front to kick off the mesylate from the back. So is this sulfur thing going to be dashed or wedged? This was dashed, going away, so now the wedged is towards us. It's the stereochemical consequence of the SN2 reaction. And there we go. There's the product, and then maybe Na plus, OMS minus. Na plus, OMS minus. Of course, OMS minus is O minus, S, double bond O, CH3. That's the mesylate anion. Right. It's just a very stable entity because you can distribute that negative charge all over the place onto the different oxygens and stuff. Okay, so yeah, it's a good leaving group. It's an alternate to the halogens. Okay, cool. All right, more. Now we're using a different chiral substrate. Let's use K plus. And then that's potassium acetate. So it's potassium, K plus, acetate. Acetate refers to that thing. It's 2 carbons, 2 oxygens. That's a CH3 right there. And yeah, potassium acetate. Okay, so what's the SN2 product? This is just another good SN2 nucleophile. Easy mechanism. Attacks, kicks off the BR. Now what's the stereochemistry of the product? BR was wedged, the acetate is now attached and is dashed. What's the functional group we just created? An ester. So one of the ways you can make esters is by an SN2 reaction. What's the byproduct in terms of the spectator ion and the leaving group? KBr, potassium bromide. KBr, okay. One more. Benzene CH2 iodine. Alright, sulfur with a negative charge is always a good nucleophile. That's a general rule. Thiolate. Thiolates are S minus things, just kind of generic S minus things. What's it called if you have an SH? Like if this wasn't S minus, but it was like isopropyl SH, that'd be called a thiol. Remember that? Thiols are things that have an SH, and they stink really bad. Okay. Anyway, what's the SN2 reaction that would occur here? Well, circle lone pair, kick off leaving group, and then we got that. What's the name of the functional group we just created? Looks like an ether. It would be an ether if that was an oxygen, but when it's sulfur, it's called a sulfide. Alright, great. Alright. So we're still talking about the nucleophiles. We're on number 8, SN2, reactivity, nucleophiles, the nucleophiles. Alright. Now we're on to B, which is that nucleophilicity. Nucleophilicity decreases to the right on the periodic table. Nucleophilicity decreases to the right on the periodic table. Let's draw a mini version of the periodic table from memory. I'm just kidding. I barely can recite much of the periodic table, but a couple things, like if we look at the second row atoms, kind of on the right, they go boron, carbon, nitrogen, oxygen, fluorine, and neon. So as you go kind of from the left to the right, nucleophilicity decreases. So like carbon to nitrogen to oxygen. And that's going to be mostly due to nucleophilicity correlating to basicity. And so let's show an example of that. So strong bases are better nucleophiles. What we're going to find, for example, is that nitrogen is a better nucleophile than oxygen, and that's due to nitrogen being a better base. So H3N, we'll use bromoethane, and we're going to compare H3N versus H2O as nucleophiles. What are the products of these reactions? I mean, if nitrogen attacks, or oxygen attacks, we kind of saw these examples already, but let's compare them side by side now. And so you would get NH3 plus, Br minus, OH2 plus, Br minus. Alright. And what did we say was going to be the faster one? If nucleophilicity decreases going to the right, that means between nitrogen and oxygen, who's going to be the faster one? Probably should be the nitrogen's going to be the faster one because it's on the left. So that's true. Faster, slower. Okay. So the nitrogen is faster. The basic reasoning, like I said, nucleophilicity correlates with basicity. Okay, so stronger bases or stronger nucleophiles? Weaker bases or weaker nucleophiles? More basic. We could say that more basic gives you a more reactive lone pair. Has more likelihood to go attack stuff, or maybe even get a proton. That's that's the same idea. What things that are bases will either seek out a proton or go attack an electrophile, right? And more nucleophilic. Less basic. Things that are less basic are going to have a less reactive lone pair and be less nucleophilic. Okay, cool. One other easy way to think about this, I'll show it right here. Okay, so we know that nitrogen's on the left of the periodic table and oxygen's a little bit on the right of the periodic table, right? So if nitrogen's on the left, does that make it more electropositive or more electronegative? Nitrogen's on the left of the periodic table relative to oxygen. Does it make it more electropositive or electronegative? The answer is this can be a little more electropositive, and being a little more electropositive will stabilize it a bit more, right? So N plus will be a little more electropositive than O plus, and that also kind of stabilizes it. And that's another way to explain that it's actually a faster reaction, is the electropositivity of nitrogen. Okay? I'll just write that at the bottom. So also, nitrogen more electropositive. Oxygen. And that'll stabilize the product when the nitrogen attacks just a little bit more. So that's another explanation. Okay, so we're still talking about the nucleophile. And let's just discuss that just a tiny bit more. That why ammonia NH3 is more basic and more nucleophilic and more nucleophilic than water. The book goes into a little more depth, and we don't really need that much depth. But we can show this quantitatively. So if I consider the nucleophile, the nuke, what are the nukes that we just considered? The nucleophiles, we considered H3N and H2O. Okay, what are the conjugate acids of these things? Because you can't we can't directly consider basicity of these quantitatively using pKa's. pKa is like a very universal method. A pKa is a very universal method for acidity, right? But we don't want the acidity of these guys. We would want the acidity of the conjugate bases, and that'll give us a sense of the basicity. Maybe that'll make sense in a second. All right. So the conjugate acids are what? Conjugate acids of these two things. What are the conjugate acids of these two things? Well, how do you determine the conjugate acid of something? It's H4N. You add a proton. And then the conjugate acid of water is H3O plus, right? Okay. So when we consider pKa values, right? We need to use the conjugate acid of something to show the pKa of it, and that'll tell us something about the relative basicity of these things. Now there's also a pKb scale, but nobody really uses pKb. Everybody uses pKa. That's why we're kind of contorting ourselves a little bit by doing this operation so that we can talk about pKa's, because pKa's are just very universal. Alright, what are the pKa's of ammonium and hydronium? Well, now we have a big difference, 9.3 and negative 1.7. What does that tell us about the acidity of these two things? Who's more acidic? Who's more acidic? Well, the lower pKa is more acidic. So that's much more acidic, and that kind of refers to the relative, this being very, very acidic. What does that tell you at this? Is it a stable thing or a kind of unhappy thing? This is such a strong acid, lose the proton, and does it make a stable thing or an unstable thing? And that is actually a very stable thing. We know water to be very stable, right? On the contrary, pKa of ammonium is 9.3. So is that very acidic? That's not very acidic. What that means is that what that reflects is the stability of this NH3. This is very stable. What about this? Is this very stable? Relatively speaking, because it has a high pKa, it really wants to be protonated. It doesn't want to give up that proton the way that hydronium does, right? So the high pKa tells you that this thing's unstable and also more basic. So this is going to be a strong base and that's going to be a weak base. That's kind of what the pKa does here, right? So basicity of A, which, and by A I mean the left thing, okay? And the conjugate acid is HA. Alright, there we go. So this, the A refers to NH3 or water. Conjugate acid, HA, refers to these guys with an extra proton. And then the pKa refers to the pKa with the conjugate acid. So now we consider the basicity of A. And who's the strong base and who's the weak base? This is the strong one. Stronger and weaker. Okay, and end result was that NH3 is a better nucleophile, right? It's a better nucleophile because it's a stronger base. That's it in a nutshell. This is a strong base due to the high pKa of its conjugate acid. This is a weak base due to the low pKa of its conjugate acid, okay? And the basicity of the stronger basicity of A, NH3, was it due to the nucleophilicity? It's a better nucleophile. It's a stronger base and it's a better nucleophile. Okay, whoops, sorry. Okay, so anyway, that's kind of a rationale for why NH3 is a stronger base and a better nucleophile. Okay. Book goes into a little more detail, but this is sufficient for us. Alright, now we're on to C, 8C, which is that nucleophilicity increases going down the periodic table. Increases going down the periodic table. Nucleophilicity increases going down the periodic table. Let's show some examples and just do which leaving group was that? So one of our fancy leaving groups with the methyl. It's called mesyl. Okay. Now we're just going to show a series of nucleophiles going down the periodic table. Mesyl or OMS. So F minus can attack, kick off the leaving group, and make fluoropropane. And then we'll show more. Going down the periodic table. Chloride. Chloride kicks off, this is the same thing, right? OMS, yeah. Chloride does the same thing. And OMS minus. And then bromide does the same thing. And iodide does the same thing. Okay, and I'm not showing like a counter ion, but you could do like sodium plus F minus, sodium plus chloride minus, etc. But we're kind of skipping that part. Now, what did we say? Nucleophilicity increases going down the periodic table. So here's the fast one. Here's the slow one. Choose the fastest, choose the slowest. Because if it increases going down the periodic table, that must make this the fastest. And that must make this the slowest. Okay. So iodide's the fastest, fluoride's the slowest. And why is that? Why is that? Well, we talked about large things. We talked about large things and the effect of those large things on like charge density. And we even gave it a name. Remember the weird name we gave for large things like iodide or phosphorus or sulfur? It began with P. Remember that word? It was polarizability. So the answer is polarizability. Polarizability of the nucleophile. And polarizability basically refers to a large surface area where the charge can be distributed over the large surface area. Iodide definitely has that. Fluoride does not, because fluoride is really tiny. And so we can draw that also. And kind of the the effect of polarizability in terms of the nucleophilability. So here's F minus, really tiny. F minus is really tiny. What about iodide? Iodide's huge. They both have a negative charge on them, right? So the main effect of the polarizability in terms of the nucleophile structure is that F minus, it's got a very concentrated charge density, and when you have a solvent like methanol or something dissolved around it, you're going to be blanketed in solvent. These are all methanol molecules. Book shows this too. Maybe look in the look in the book for maybe a nicer figure. But you have solvent all over the place, and the F minus is actually hydrogen bonding to all the H's. So maybe I should draw the H a little better. F minus, and the H's are all delta plus. Redraw this a little bit better, sorry about that. There's a lot of hydrogen bonding between the F minus and the H's. And F minus is blanketed around solvent. And do you think that's going to really make it nice and happy to go react with stuff and go attack stuff? The answer is no. It's really excited just talking to all these H's around it, and like water molecules and methanol and things like that around. Now you also have that here, but there's less of it. So there's a little bit of iodide, interacting with the H's, but for the most part, iodide is free to react. Because the charge is distributed over a larger surface area, and there's less of this interaction with solvent molecules. Okay, so that's a reason for what we showed above, which was that things like fluoride and really tiny things react slow, and as you go down the periodic table, they get faster and faster. And there's less of these solvent interactions. Okay, great. And the book has a figure kind of like this too. Okay, so continuing talking about the nucleophile and how the nucleophilicity increases going down the periodic table. Another example. Let's consider a different atom, like O-. And this is a nice SN2 reaction. That is a nice SN2 reaction. Okay. What's the mechanism? What's the product? You can just circle the lone pair, kick this off. Makes what kind of functional group? What kind of functional group is that? It's called a ether. So this is one of the best ways to make ethers. You can almost make any ether in the world this way. We'll learn later. It's called the Williamson ether synthesis. Williamson. It's so common that it has a name. You could probably Google that and see 1,000 examples of the Williamson ether synthesis. Okay, what's under oxygen on the periodic table? Sulfur. Okay. And what would that reaction be? Pick a lone pair, circle it, attack, break the leading group off, and you get that. What do we call this? It's called sulfide. Remember, ether, sulfide is the analog of an ether that's based on sulfur. Okay. Which of these is faster, based on what we just mentioned? Which of these is faster? Going down the periodic table makes it slower or faster? Makes it faster. So this is gonna be faster. This is a little slower. And just to keep the trend going, what about what's under sulfur? If I have to look on your periodic table, what would be under sulfur? It's another S thing, but it's selenium, Se. And what if you have ... negative, and you do the same exact thing? What would you get? You get that. If this is an ether and this is a sulfide, what do you think this is going to be called? Sulfide, selenium, selenide. Different functional group. Selenide is the selenium analog of a sulfide. Okay, and it's lower on the periodic table, so is it going to be faster or slower? lower on the periodic table, faster. So this is actually the fastest of all three of these. Fastest, slowest, this is medium. Okay, slowest, medium, fastest, okay? I think I gave names for these kind of things too. What's this thing called if it is something O minus? Something O minus is not an alcohol. Let's just give a name for that. Because you will see that 1,000 times. It's called an alkoxide. Alkoxide. So things with an O minus are called alkoxides. Things with an S minus are called thiolates. And thiolates are pretty good nucleophiles. Yeah, definitely better of a nucleophile than the oxygen thing. Thiolate, I'm not too sure what this is called. Selenate or something? I'm not sure. I don't know. But the most common ones are alkoxide and thiolate. Okay? The other thing, I guess, putting this all together now, is this a little bit of a weird result. Considering, you know, you get different rate effects if you go across the periodic table and down the periodic table. So, but it's not. It's just, you know, they're different effects. All right. So we get when you go across the periodic table, you we explain this with increased basicity. So increased basicity explains why ammonia is better than water. Because ammonia is a better base, okay? But as you go down the periodic table, you actually create weaker bases. So it's kind of weird, because we know that if we go down the periodic table, it's more nucleophilic, right? And also decreased basicity. You go down. So this is almost like increased basicity only explains when you go across the periodic table why ammonia is better than water. But as you go down, it's not basicity that explains it, it's increased polarizability. Increased polarizability explains why you get like iodide is better than bromide, better than chloride, better than fluoride. So fastest, slowest. And also why like selenium is better than sulfur is better than oxygen. Same kind of thing. Okay? So differing explanations for if you're going across the periodic table and if you're going down the periodic table. And that's chemistry for you. There's not like some universal explanation. Okay? It's a little weird, but not that weird. Okay, so another thing about nucleophiles and nucleophilicity is going to be D, and that's the effect of protic versus aprotic solvents. The effect of protic versus aprotic solvents on nucleophile ability. And the immediate question will be, what is a Protic solvent? What's an aprotic solvent? You might be able to make a guess, because Protic kind of sounds like proton. Aprotic sounds like maybe no proton. And that's actually a pretty good guess. Okay, so these are going to be considered like two different kinds of solvents. So two kinds of solvents. Okay, that we're going to consider. And the first are going to be called polar Protic. Polar Protic. And when I refer to Protic, what I really mean, well, polar, we know polar, so that's to have some kind of polar structure, like polar functional groups or something like that. Protic, though, refers to hydrogen bond donor, HBD. It has to be hydrogen bond donating. Okay. So what's an example of a polar solvent? A polar solvent that's Protic, and you might be drinking it right now as you're watching this lecture. Maybe water. Water, that would be a good polar Protic solvent. It says polar because you have the oxygen is delta negative, H's are delta positive, and the hydrogens are hydrogen bond donors, right? They donate hydrogen atoms. What other things are there kind of like water that are simple functional groups? I don't know. Methanol. Methanol is also very similar to water in this chemical structure. You just have a carbon there. And maybe ethanol, right? All of these are polar Protic solvents. Alcohols, water, and you can also say they are all hydrogen bond donors. Hydrogen bond donors. What do we abbreviate that as? HBD. Okay. So polar Protic solvents are like water and alcohols. They can donate the proton through hydrogen bonding, right? The proton is kind of donatable. Okay. And then the other ones we're going to consider are polar aprotic. Polar aprotic. And those are ones lack a hydrogen bond donor. Lack an H bond donor. They lack a hydrogen bond donor. Okay, so but they are polar. They have a polar element, maybe a polar functional group. They're usually organic solvents. I think they're always organic solvents. Okay, very simple one. What's this molecule called? What functional group is it? What functional group is that? It ends in ONE. It's a ketone. It's a ketone functional group. And this specific molecule has a name. It is a ketone functional group, but what's the name of the molecule? You may remember it when we introduced ketones, but it's called acetone. Acetone's a 3-carbon ketone, very simple molecule. Okay. What about this? It's a 2-carbon molecule with a, what kind of functional group is that? So that's a ketone up top. This is called a something ILE, something IL. It's a nitrile. And this specific molecule is called acetonitrile. Acetonitrile. So these are polar aprotic solvents. They do have protons in them, but none of these are hydrogen bond donating protons, right? None of these are like OHs or NHs or anything like that, right? Whereas up top, the polar Protic ones had OHs. These are not. These are like CH3s and stuff. Okay, more. There's more. This is a very classic one. We use this all the time in the laboratory. What functional group is that? C double bond O next to nitrogen. It's an amide functional group. And the name of the molecule is dimethyl formamide, F-O-R-M, amide, or amide. Formamide though, we call it dimethyl formamide. Nice abbreviation, DMF. Dimethylformamide is a nice polar aprotic solvent, and we'll see that these work really well for SN2 reactions. Okay, let's keep going. DMF. And then we have another weird one. Kind of looks like acetone. But with a sulfur in it. I don't think you learned this functional group. S double bond O. It's kind of like a ketone, right? It's kind of like a ketone, but this is called a sulfoxide. And this molecule is called dimethyl sulfoxide. You may know the abbreviation of this. You may have heard of it somewhere or other. DMSO. DMSO, dimethyl sulfoxide. Okay, I think I'll show one more. These are all kind of commonly used polar aprotic solvents for SN2 reactions. Okay, what's going on here? What's going on there? And is any charges missing? We have nitrogen bound to 4 things, so the charge must be positive. And then we have this oxygen bound to 1 thing with 3 lone pairs, and it is negative. Okay, and the name of that functional group, we didn't list it when we learned functional group names, but it's a carbon with an NO2 group. Carbon with an NO2 group, that's called a nitro group. This NO2, it's called nitro on methyl. We call this molecule nitromethane. Nitromethane. So these are 5 different polar aprotic solvents. 5 different polar aprotic solvents, alright? Okay, so I just want to close with a really cool experiment that sort of shows, you know, what's the effect of these polar aprotic solvents or polar aprotic solvents on SN2 reactivity. You know, why does it matter? Why does it matter if you have a polar protic or a polar aprotic solvent? So I'm going to show a little chart to show this example. Okay, so we're going to do, I'll summarize and just say that polar protic are slower, and it's due to extensive H bonding. Hydrogen bonding, okay. So if the polar protic are the slow ones, you're going to be the fast ones. The polar aprotic. Okay. In the amount of time I have, I'm probably going to just wait till next time. But I'll just show an example of, like, you know, how you would write a polar aprotic solvent being used in an SN2 reaction. I will just draw like this. K plus, Cn minus. Of course, that's a very simple K plus, Cn minus. It's a triple bond N. C triple bond N, right? K plus, C triple bond N. And if we use any of those polar aprotic solvents, the reaction goes super fast. And we'll explain why next time. Okay, so which one should I use? What's your favorite one from the list? And just think of an abbreviation for one of them. Normally, like in class, like in a normal class, I would say, what's your favorite SN2 solvent? Because all of those polar aprotic solvents work really well. The common ones that are easy to remember probably are DMF and DMSO. because there's simple abbreviations. So yeah, DMF or DMSO work really well. You just write them under the arrow or something, and that would facilitate the reaction to make the nitrile, and then KBr. And the mechanism, of course. Okay, and yeah, so I'm going to explain why the polar A Protic solvents are so much better next time. But the quick summary, though, is that, as you might imagine, the Protic solvents have extensive hydrogen bonding because they have a hydrogen bond donating, you know, OH or something. And that's why the polar Protic are really slow. Polar A Protic do not have that issue, and yeah. So anyway, I'm going to stop now, and we will continue this discussion next time. And just for now, remember polar A Protic are good, and maybe remember a couple of them, like DMF, DMSO, as good SN2 solvents. Good solvents for the SN2 reaction.